Okay, let's finally do some conservation of momentum problems. One of the biggest applications of conservation of momentum is rocket propulsion. And you're like, wait, there's no collision. Like, how is that a conservation of momentum problem? Well, if you guys will go to the rocket propulsion slide, I will tell you. So think about it. You have this rocket, okay, that's like sitting on a launch pad, just sitting there, right? And it's not doing anything. And then suddenly, right, so by not doing anything, that means that the momentum is zero, right? And suddenly, there's this ignition of gases, right? And all these high energy molecules are being fired out the end of the rocket, right? Those molecules, they have a mass and they have a velocity. So each one of those molecules has a certain amount of momentum, okay? And so for every molecule that's fired away at a certain velocity, it must be an equal amount of momentum supplied to the rocket itself so that momentum stays conserved. Okay, this is a lot of the same reason why the squid we talked about earlier is actually able to move. It's the same kind of thing. It's the same kind of reason why if you're on a stand-up paddleboard or if you're surfing, you push water back, you're giving that water momentum, right? Which in turn, in order for momentum to be conserved, gives you a momentum forward. So water has momentum back. That means that you then have momentum moving forward, okay? So the whole reason why we are able to put things up in space is because momentum must be conserved between the actual rocket and the gases that are coming out from the end of the rocket, okay? And so I want to kind of look at the same principle, but with a little bit more of a playful example. I may be now officially dating myself with a movie like this, but this is movie Blades of Glory with Will Ferrell and Jon Heder. They're ice skating champions. And so in this video, they're doing like a duo tandem dance, okay? And they push off each other, okay? So if we imagine that there are a couple of skaters, right? And I guess looks something like that. Here's another skater. Right? And initially, so this is one or before, right? Initially, they're just standing there, maybe kind of like, just making contact, right? But not moving. Neither one's moving. And then afterwards, they push off each other, and they start heading off in different directions. And very meanly, I made their arms go away. Why did I do that? I don't know. Okay, so now they're heading off in different directions. And they also, in this case, have different masses, right? Will Ferrell, he's a little huskier. He's got a mass of 73 kilograms, right? And we have Jon Heder over here who has a mass of 51. So I'm going to say mass of Jon, mass of Will. Okay? All right, so how can we use conservation of momentum to find out what the speed of Jon Heder will be as he's flying away, or any two ice skaters in the world? Really, this could be any two ice skaters, right? And so we know that the speed of Will Ferrell when he pushes off is 2.01 meters per second, okay? And these guys are pushing off from each other. And this is a prime example of conservation of momentum. We know that the momentum 1, or momentum before, must equal momentum 2, or momentum after, okay? So let's look at this. What momentum do we have before? Well, we have the momentum of Will Ferrell 1 plus the momentum of Jon Heder 1, and then the momentum of Will Ferrell 2 plus the momentum of Jon Heder 2, right? But here, they're at rest. They're both at rest, just, kind of ready to just push off each other, right? So this whole thing here is just 0, right? And so just like we did with conservation of energy, the next step would be, let's just substitute the equations in. So this would be the mass of Will Ferrell 2 times the velocity of Will Ferrell 2, right? Plus the mass of Jon Heder 2 times the velocity of Jon Heder 2, okay? And if remember, this is what we're looking for here, right? This is what we're trying to find, because we know how fast Will Ferrell's going when he slides away, right? So this just means that negative mw2, mass of Will Ferrell, times vw2 must equal the mass of Jon Heder 2 times the velocity of Jon Heder 2. Okay? Let's just substitute those values. So we have Will Ferrell flying off in this direction. Notice this is the negative x direction, so I have to put a negative sign there. that negative, so we'll have negative times, what is the mass of Will Ferrell? Well, 73, right? Times a negative 2.01, right? These guys are going to both become positive, negatives cancel, right? And then John Heder weighs 51, right? And we want to find out what his velocity is, okay? I find this to be, putting in all my calculators, blah, 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 I get 2.9 meters per second, okay? All right. As we should do with most problems, the first thing we should do is ask, does this make sense? And here's the thing. We know it's a little bit bigger than Will Ferrell's speed when he pushes off, right? Does that make sense? Should it be bigger? And here's the deal. We notice that Will Ferrell has more mass than John Heder, right? So in order to compensate, in order for the momentums to be equal, the guy with the lower mass must have a greater velocity. And we see that that is actually what happened. And so we're like, I can probably depend on that answer, all right? If John Heder got a lower velocity, it would be a little bit weird. And if he got a tremendously huge velocity, that would also be weird. But it's a little bit bigger, and we can have some faith in it, okay? So this is a first example of how conservation of momentum plays out. Just like with conservation of energy, you say the initial momentum equals the final momentum, right? You write down what momentums you have. I know that I had these two guys before and I have these two guys afterwards, right? And then I noticed that before they did not have any velocity whatsoever. That means the momentum has to be 0. So basically, these two momentums that I'm left with afterwards have to be equal and opposite in order for you to have conservation of momentum. Okay? All right. In the next video, we're going to see how do we do this when we have collisions in 2 dimensions, okay, or a conservation of momentum in 2 dimensions. Remember, momentum, unlike energy, is a vector, okay? So we have to take into account the directions, and we have to make sure everything's broken up into x and y components, and I'll show you that in the next video.